We expect our software to fail gracefully with a clear error message, but sometimes the entire system shatters. This happens when you take a high-level JavaScript engine, like Bun, and wire it directly into a low-level, high-performance systems language, like Zig. Connecting these environments is the Foreign Function Interface, or FFI. It acts as a narrow bridge translating data types between languages. If that translation is off by a single byte, the bridge severs, and the engine immediately panics with a SIGSEGV error. Even if the process survives initialization, it might crawl. You might watch a single execution tick take a grueling 3,500 milliseconds. Worse, the data itself begins to drift, silently accumulating mathematical errors over hundreds of generations while the program keeps running. The memory safety guarantees that Zig provides and the garbage collection that JavaScript relies on end completely the exact millisecond data crosses this boundary. When engineers see these cascading failures, they often blame the compiler or assume they've hit an unpredictable anomaly in the runtime. Debugging a high-performance system at this level requires discarding standard testing suites. You have to map the layout of your data byte by byte. In this specific architecture, 3 fatal structural cracks were causing the collapse. First, stack bloat. Second, memory aliasing. And finally, out-of-bounds access. High-level profiling tools cannot see across the language barrier to diagnose these issues. To fix them, we have to manually reconstruct the raw byte-level layout of the memory. The first suspect is in the main.zig file, right where the entity arena structure is initialized. This structure holds the processing data for all entities in the simulation. Combined, it has a memory footprint of 1.2 gigabytes. This diagram illustrates the mismatch. We have a massive 1.2 gigabyte block of data trying to force its way into a standard Linux OS thread stack, which is strictly capped at 8 megabytes. To clear this memory for use, the developer called std.mem.zeros, a standard Zig library function. Because of how the Zig compiler tracks compile time mutations, it forces this entire array to materialize locally on the thread stack before moving it to its final destination. The 8 megabyte pipeline instantly ruptures under the pressure of a 1.2 gigabyte allocation. The operating system kills the process, resulting in our segmentation fault. We neutralize this by bypassing Zig's implicit initialization abstractions entirely. Instead of std.mem.zeros, we use a pointer-based @memset command. The 1.2 gigabyte block bypasses the thread stack pipeline completely, routing directly to a stable storage area known as the .bss section. Addressing this memory directly avoids the thread stack limit. Implicit initialization is a useful abstraction in isolated code, but it hides hardware realities. Across an FFI boundary, standard library functions easily become lethal traps. With the segmentation fault resolved, the system runs, but a secondary failure emerges. The output data slowly corrupts over time, poisoning the simulation. The source of this anomaly lies inside the evolution.zig execution loop. This grid represents eval scratch, a temporary memory space allocated for data processing, divided into 4 distinct parking slots labeled 0 through 3. During each tick, the evolution function assigns its repacked input data directly into the first available space, filling slot 0. Immediately after, the system calls a function named runComposition, which requires its own temporary space for an initialization buffer. The collision happens here. runComposition is hard-coded to use the exact same memory space. The new data pattern overwrites slot 0, scrambling the original repacked input. Later in the pipeline, measure compression attempts to read the input. It unknowingly reads the perturbed graph output instead of clean data, permanently poisoning the fitness landscape over the next 500 ticks. To fix this logic corruption, we physically isolate the memory lifetimes. We expand the scratch array to include a 5th slot and strictly hard assign the repacked input variable to slot 4, preventing any overlap. Aggressive memory reuse is highly efficient in isolated environments. Without strict spatial ownership, it becomes a silent vector for algorithmic death. The final logic error is a phenomenon called Gaussian poisoning, found inside the measure invariance function. This function applies a Gaussian noise perturbation to the data and includes an optimization to exit early if it encounters a 0-step computation chain. Exiting early fails to trigger the code that restores the original graph features. The random Gaussian noise is permanently baked into the entity's state. We apply a surgical fix, wrapping the restoration logic in a SIG defer block. This guarantees the original state is restored across all possible exit paths, regardless of when the function terminates. With the data clean, we address the 3500 millisecond execution time. The existing 8192 edge cap was functionally useless, as it scanned linearly and missed the actual graph topology. The bottleneck is the topological data analysis. This area chart shows a node cap of 256, forcing an O of n squared sorting primitive, generating 500 million comparisons per call. Reducing the cap to 48 violently flattens the curve, shrinking data points to 640,000. Algorithmic complexity multiplies the impact of any boundary flaws. Shrinking the constant mathematical factor is exactly as critical as fixing the underlying memory logic. Looking back at our bridging channel, the data transfer between BUN and SIG is now clean, uninterrupted, and synchronized. Peak stack pressure has dropped from 6 megabytes down to 1.5 megabytes, and the evolution loop executes deterministically. A system that reliably crashed in 3.5 seconds now operates as a highly performant computation substrate. In systems engineering, there is a reverence for the mythical bug hunter, the engineer who can stare at a crashing codebase and immediately spot the flaw. This capability is simply the grueling accumulation of scar tissue. It is the result of repeatedly mapping these exact memory structural cracks across language boundaries. Surviving the FFI threshold requires abandoning high-level assumptions. It demands manual boundary enforcement, exact spatial ownership, and a ruthless byte-level paranoia.